So today I want to go back a little bit. I want to talk about torque diagrams. I want to talk about some ways to graphically solve some of these problems we have with torque. And I think it's good for us to go back and think a little bit about 1D mechanics, because we'll see that in the end we're not doing anything new with torsion. And I want us to think about our uniaxial problem, and I'm going to draw just a simple beam here, and it's going to be fixed on one end. And let's say we apply some loads to this beam. So I'm going to have a distributed load here, and we'll put some values on this later. So that we have a distributed load there. Let's say we have a concentrated force here, and then let's say we have another distributed load that looks something like this on the end. Now, and this one's going to be going backwards. Now, if we were to solve for our differential equation for this 1D rod, we would have to break it into a bunch of different pieces, because of course the distributed load changes. We have this concentrated force, and this would end up being quite a big piecewise function in order to solve for our displacement along the length. But there's a simple way that we can do it as long as we have a statically determinate system. So let's just, for a recap here, so statically determinate. So that means we have the same number of support reactions as equations. So remember, in statics, we have our three tools. We have some of the forces in X, some of the forces in Y, and some of the moments. In 1D, we don't have three anymore. We only have one equation. And that, in our case, we're going to say is some of the forces in X, if we assume that this is the X direction. And that means we can have, at most, one support reaction. And this is exactly like torque, so this will come into play as well for when we talk about torsion. So this is the same as torsion. In torsion, remember, we just have our sum of the moments about the axis. And so this is what we're going to be talking about today. We're going to be talking about statically determinate systems, so we'll put a star on that. What's the opposite of a statically determinate system? Is an indeterminate one. And in 1D, we looked at these, right? We would have two fixed ends, one on either side. And what we're really saying here is we have more reactions than equations. And this is when you need to use governing equations. Essentially, we need to have more, so this requires more information about the system, specifically about deformations. So you need to have some idea of the stiffness of these elements so that you can determine the motion that will occur. So whenever we have an indeterminate system, we have to do something involving our governing equations. We have to solve for those values in a different way. For something like this, where we have a statically determinate system, there's a lot more tools that we can use, and in a lot of ways, this will be useful in a lot of different situations where you have these types of simple problems. And what I want to talk about is, instead of going through this and thinking about equilibrium, instead of thinking about it in terms of our differential equations, we're going to think about it in a graphical way. And so we're going to talk about the graphical method for this. And I am going to write down a number of steps here. So this is kind of just a sequence of steps to allow you to draw the axial force diagram, and then in the next video we'll talk about how you can use that axial force diagram to figure out the deformation. So the first step, we've already done some of that, and that's going to be to draw the rod, so the system that we're using with, the supports, which we've done, and the loads, I suppose, would be good too. And we should put some values on here. And so I'm just going to give these guys some numbers. We're gonna say that this is going to be 5 kips per inch. We're going to say that this value at the peak is 5 kips per inch as well. I'm going to say that this force here is 150 kips. And we can, I think that should, we need some distances here. So let's do that in just a moment. We've now gotten our step 0 done, first part. The next thing is what we want to do is we want to draw lines down from the loads. So those are concentrated loads, the supports, and the start and end of distributed loads. So I'm going to do that with my green pen here. And let's draw this line, something like that. So here's my first line down. Now I'm going to be at the end of my distributed load. So I'll draw another line down. And I'll come over here to my concentrated force. I'll draw another line down. I have the start of my distributed load here. And then I have the end of my distributed load and the end of my beam. So I'll draw one more line there. Okay, so that's the second piece of step 0. Step 1 is going to determine the reactions. So we need to know what is happening over on this end. And so we have some reaction over here. And we would put it in the positive x direction for now. And then we would do our sum of the forces. And x, we know those are going to be equal to 0. I would need to tell you some of these dimensions, which would be helpful. So we're going to say, we'll draw some lines across here. Let's just do it that way. And we can talk about some of these lengths. So this is going to be 10 inches. And we have another 10 inches. And we have 20 inches. Oh, I didn't draw this to scale very well. Sorry about that. And that's 40 inches. This is just a nice little problem. The numbers don't really matter, but the idea and concept will be good. So if we think about some of the forces here. This is 5 kips per inch times 10 inches, so that's 50 kips. We have 1/2 times 40 inches times 5 kips, so that's 100 going to the right, sorry, to the left. This is 50 going to the right. This is 150 going to the right. So we have 200 going to the right. We have, this is 100 going to the left. So RA is going to need to be 100. And it's going to be needing to go to the left. So we would say RA is equal to negative 100 kips. So we could maybe scratch that off. I'd be going that way. Okay. So now we have our reactions. That was step 1. In this case, it's statically determinate, so we should only have 1. And we figured that out. And now we're on to step 2. And the graphical method here, I want to make sure you guys can read it. So starting from the left end, we're going to go from left to right. So we're going to start at this line. We're going to move across to this line. And then I should draw out my axis here. So my axis is going to look something like this. There's my axis. We're going to start from the left side. We're going to move to the right side. And we're going to construct our axial force diagram. And there's a couple of different things we're going to do. So anytime we have a concentrated force. Concentrated force. That's a force. So these are going to happen at the lines. And anytime we see a concentrated force at the lines, we're going to shift in the opposite direction. All right. And between the lines now, so this is going to be between the lines, the slope of the n of x is given by the opposite of b of x. And remember, mathematically, we had our governing equation, and it said that dn dx is equal to negative b of x. So that's just a result of that equation. The third thing that we're going to do is that the change in value of n of x between the lines is the area under b of x curve. I just squeezed it in there. So I wanted to make sure we went through these steps, but I think it's very hard to visualize this unless you see an example at the same time. So in this case, we're going to do an example right at the same time. That's what we're seeing here to our left. So let's go through this process over here. We determined our reactions, and now we're going, oops, I bumped the camera, sorry about that. Now we're going to determine our n of x diagram. So let's put that here. There's our axis. This is n of x. This is going to be x. And let's go through our steps. So we start off at a line, right? That's at the left end. And we come up here, we say, aha, do we have a concentrated force? The answer is yes. We have our reaction. And we're at a line. A concentrated force at a line shifts the diagram in the opposite direction. So of course we start off here at 0. We have a negative 100 kip force here, which means we are going to shift up, which would be positive, an amount of 100 kips. Okay, so this would be our value. That's 100 kips. Now we're going to keep moving to the right. Now we have we have a distributed load in between this line and the next one. And we know that the slope of the n of x curve, so that's what we're drawing here, is given by the opposite of b of x. Okay, so now we think about our distributed load here. Our distributed load is pointing to the right, which means it's positive, which means the slope is going to be negative. So that means we're going to have a negative slope here. And we should have a negative slope on this side as well, because b doesn't change. It's always the same in this interval. The change in the value of n of x between lines is going to be given by the area under the b of x curve. So this is a constant. So the area underneath the curve is the value of the constant times the distance. So that's 5 kips per inch times 50. Again, it's the opposite. So we're going to go from 100 minus 50, 5 times 10, down to 50. So we're going to go down to here, and at this value we're going to be at 50 kips. Okay, now we're going to think about what's happening between these two lines, and we don't have any distributed load up here, so that means we're not going to have any change. We're just going to go straight across. And we've gone straight across. Now we've gotten to this line. What's happening at that line? Well, we have a concentrated force. So we go back to our first part here, part A. The concentrated force is to the right, which means it's positive, which means the shift is going to be negative. And so now we're going to come down and we're going to come to negative 100. Okay, now we look at this next interval. We see we don't have any distributed load in that interval, which means we won't have any change in our n of x diagram. We can draw a line straight across. And now we get to our final interval. There's no concentrated force, so there's no shift here. But now we need to figure out what the change is going to be from the left side to the right side. We again think about the slope of the n of x curve. We see here that this is going to end up being a negative b, right? B of x is in the negative direction, which means the opposite of that is positive. So this is going to tell us something about the slope, and it's going to be a positive value. At the left end, the slope is going to be 5 kips per inch, which means we're going to have something that looks like that. On the right end, the slope is going to be 0 because the value of b of x is equal to 0. So we can draw that here. Now, what happens in between? Well, this is a linear slope, right? We know that b of x is the derivative of our n of x, which means if this is linear, that means this must be quadratic. And so what we are going to see is that we should have a quadratic curve here. The change, I've drawn that line there. We could have drawn it anywhere. We don't quite know where it is yet, but we should be able to calculate what the change in the n of x diagram is from the left to the right side by looking at the area under the b of x curve. This is 5 kips per inch times 40 inches times 1/2 because it's a triangle, right? It's a simple shape, it's a triangle, and that ends up being 100. So again, the value is negative, which means that we're going to add 100, so we're going to do the opposite. And so that means we're going to go from negative 100 to 0. We're going to have a slope 5 here of 0 there, and so we should end up with a curve that looks like that. And so there you go. Now we've drawn our axial load diagram. We could down here then divide that by A to get us from our internal force to our stress. Once we have our stress, we could then calculate the strains, everything else from there. And what we'll do on the next video is talk about the displacement.